Welcome to the lecture number 2 of FX controller. In this lecture, we learn about the TCSC FX controller. TCSC means Thyristor Control Series Capacitor. So in this lecture, we learn about the introduction of TCSC, basic operation of TCSC, practical module of TCSC, different modes of TCSC operation, and the VI characteristics of TCSC. So first of all, what do you mean by series compensation? Because TCSC is a series FX controller. So in series compensation, the FX devices are connected in series with the power system transmission line, and it works as a controllable voltage source. And in long transmission lines, the series inductance occurs that causes a large voltage drop when a large current flows through it. To compensate it, we add series capacitor. It is connected between the transmission line, which modify the line reactance by decreasing its value. So your line reactance is decreasing, and therefore your power transmission capacity is increased, because as we know that the P is equal to V1 V2 by X sine delta. So if your X is decreased, then your active power transmission is increased. However, more reactive power must be provided during the series compensation. So this is a basic module of TCSC. So in general, the TCSC sometimes maybe external may be asked, what do you mean by TCSC, or define the terms TCSC. So the TCSC means a capacitive reactance compensator, which consists of a series capacitor bank shunted by a Thyristor controlled reactor in order to provide a smoothing variable series capacitive reactance. The TCSC rapidly adjusts the system impedance. It introduces variable inductance or variable capacitive reactance in the transmission line. So the main and basic objective of TCSC in power system is to enhance the power flow and improve system stability. The deployment of TCSC in transmission line also improves the SSR mitigation. SSR means subsynchronous resonance. Power oscillation damping means POD, and transient stability. So the basic model of TCSC comprises a series capacitor in parallel with a Thyristor controlled reactor. So the basic operation of TCSC, this is a basic figure of TCSC. A simple understanding of TCSC functioning can be obtained by analyzing the behavior of variable inductor connected in parallel with a fixed capacitor. So the equivalent impedance for this LC combination, it is equal to Z equivalent is equal to Z 1 upon omega C parallel with J omega L is equal to minus J 1 upon omega C minus 1 upon omega L. Now there are three conditions here. If the impedance of the fixed capacitor is only present in your transmission line, means there is no inductive reactance is there. So at that time, you will get the Z equivalent to minus J 1 upon omega C. Now if omega C minus 1 upon omega L is greater than 0, or in other word, omega C or in other word, omega L is greater than 1 upon omega C. So the reactance of the fixed capacitor is less than that of parallel connected variable reactor. And this combination provides a variable capacitive reactance. And this inductor increases the equivalent capacitive reactance of the LC combination above that of the fixed capacitor. The second condition, if omega C minus 1 upon omega L is equal to 0, that means a resonance develops that result in an infinite capacitive impedance. And this condition is obviously it is not acceptable. So it is unacceptable condition when the omega C is equal to 1 upon omega L. And the third combination, if omega C minus 1 upon omega L is less than 0, the LC combination provides the inductance above the value of the fixed inductor. And this situation corresponds to the inductive Vernier mode of the TCSC operation. So this is the basic operation of TCSC. In the variable capacitor mode of the TCSC, as the inductive reactance of the variable is increased, the equivalent capacitive reactance is gradually decreased, and the minimum equivalent capacitive reactance is obtained for extremely large inductive reactance or when the inductor is open circuited. This is the actual module of TCSC. There are number of LC combinations are connected in a series, so that is actual module of TCSC. And this is the practical module of TCSC. In the practical module, it includes the protective equipment normally installed with a series capacitor, which is shown in this figure. Here the MOV, it is a metal oxide varistor. It is a non-linear resistor. It is a connect across the series capacitor to prevent the occurrence of high capacitor over voltages. It also allows the capacitor to remain in a circuit even during the fault condition and helps to improve the transient stability. The next one is the circuit breaker. It bypasses the capacitor if severe fault or equipment malfunction events occur. Next is the LD. It is a current limiting inductor. It is incorporated in the circuit to restrict both the magnitude and frequency of the capacitor current during the capacitor bypass operation. If the TCSC valves are required to operate in the fully on mode for prolonged duration, the conduction losses are minimized by installing the ultra high speed switch contact or ultra high speed contact across the valve. This metallic contact offers a virtually lossless feature similar to that of the circuit breaker, and it is capable of handling many switching operations. The metallic contact is closed shortly after the Thyristor valve is turned on, and it is opened before the valve is turned off. And during a sudden overload of the valve and also during the fault condition, this metallic contact is closed to alleviate the stress on the valve. So this is the practical module of TCSC. Now we move forward of the different modes of TCSC. So normally there are 4 types of modes are there. First one is a bypass thyristor mode, second one is a block thyristor mode, third one is a capacitive Vernier mode, or fourth one is a inductive Vernier mode. So we will see each of these mode in details. So first is bypass thyristor mode. So this is a basic diagram of this bypass thyristor mode. So in this mode, the thyristors are made to fully conduct with a conduction angle of 180 degree. So gate pulses are applied as soon as the voltage across the thyristor reaches 0 and become positive. That results in a continuous sinusoidal of flow current through the thyristor valve. The TCSC module behave like a parallel capacitor-inductor combination. However, the net current through the module is inductive for the susceptance of the reactor is greater than that of the capacitor, which we choose here. So this is the basic bypass thyristor mode. This mode is employed for control purpose and also for initiating certain protection for functions. The next is a block thyristor mode. So it is also known as a waiting mode. So the firing pulses to the thyristor are blocks. So if the thyristor are conducting and a blocking command is given, the thyristor turn off as soon as the current through the reaches a 0 crossing. And TCSC module thus reduced to a fixed series capacitor because we blocking the gate pulse. So this become open circuit So only the series capacitor is connected across the transmission line. So the TCSC module is provide the capacitive reactance into the transmission line during the block thyristor mode. Next is a capacitive Vernier mode. So this mode allows the TCS to be either continuously controllable capacitive reactance or capacitive reactance. So it is achieved by varying the thyristor pair firing angle in an appropriate range. However, for smooth transition from the capacitive to inductive mode, it is not permitted because of the resonance region between the two modes. So during the capacitive Vernier mode, the thyristor are fired when the capacitor voltage and the capacitor current have an opposite polarity. So this condition causes a TCR current that has a direction opposite that of a capacitor current and thereby resulting in a loop current flow in the TCSC controller. See, this is a loop current which is flowing in a TCSC controller. So the loop current increases the voltage across the fixed capacitor, effectively enhancing the equivalent capacitive reactance and the series compensation level for the same value of line current. The last one is the inductive Vernier mode. So in this, the TCSC can be operated by having a high level of thyristor conduction. So in this mode, the direction of the circulating current, it is in reverse and the controller present a net inductive impedance. So in previous one, the loop current is the same as a line current, whereas in the inductive Vernier mode, it is in opposite direction. So that here we provide the inductive impedance. Now the capability characteristic, which is also known as the reactance characteristic of TCSC module. So before learning this characteristic, we understand the three limits for that. First one is the voltage limit. So voltage limit of with the maximum amount across any operating equipment is determined by the equipment's insulator level. And the constraint on voltage may vary with the duration of voltage application. So for short duration, the overvoltage limit of the MOV, which is metal oxide varistor, is more critical than that of the capacitor. The second one is the current limit. The current limit which may need to be imposed on the current in the thyristor, valve, fixed capacitor, and the surge inductor to prevent the overheating. Harmonics also causes heating and therefore have a constraint effect on the TCSC operation. And last one is the firing angle limit. And this limit must be carefully restricted so that the TCSC does not go into the resonance region. Because when the XL is equal to the XC, then the TCSC goes into the resonance region. So for that, we limit the firing angle of the thyristor valve. So this is the basic VI characteristic of TCSC. This is a single module TCSC. The upper portion, it is a capacitive portion, and the lower portion, it is an inductive portion. We will see each the portion in detail. So first we see the capacitive region. So the maximum capacitive reactance is chosen based on the TCSC design so that the TCSC does not venture close to or into the inherently unstable resonance point. So here we select the XC value, right? So that the TCSC module, it is not go to the resonance condition. So the maximum X TCSC is typically 2 to 3 pu as expressed in the per unit of XC. See here, the maximum value is 2 to 3 pu. Why this restriction is imposed? This restriction is imposed in the form of a maximum advance angle beta, right? And the minimum TCSC capacitive reactance is obtained when the Thyristor are blocked. So that if we operate the TCSC in a block Thyristor mode, at the time that we get the minimum TCSC capacitive reactance. And the absence of Thyristor current flow and relating to XTCSC, it is a 1 pu. As the line current increases, the TCSC voltage increases until the maximum point. See here, as the line current will increase, the TCSC voltage increase up to the maximum point. Right. So this is the basic capacitive mode. So in capacitive mode, there are no Thyristor. So no Thyristor current is there. Here we protect the capacitor. So MOV protection level is there. No harmonic because of no Thyristor switching is present during the capacitive mode. Right. Now the second one is a inductive Vernier mode. So in the inductive reactance zone, the maximum reactance limit is also selected to prevent the TCSC from operating in the resonance region. This is an inductive Vernier mode. Right. So this limit is attained at a lower line current value, and it is expressed in terms of the maximum firing angle delay. See here, at lower line current value, your voltage become a constant in an inductive mode. So the maximum inductive reactance of 2 pu is typical. The minimum inductive reactance limit is reached when the Thyristor are fully conducting, and at the time your firing angle is 90 degree. So with increasing line current, harmonics is generated. That causes not only the heating of reactor and Thyristor, but also peak voltage close to the voltage limit of the capacitor and MOV, which is indicated in a time duration. At high line current, the maximum Thyristor current in the inductive Vernier mode constrains the TCSC operation. So when your TCSC is operating in the inductive mode, at that time the harmonics are present due to the Thyristor switching. Inductive Vernier mode of TCSC operation. How can you calculate the XTCSC? So the XTCSC is equal to XL into XC upon XL plus XC. So by selecting the capacitive and inductive reactance value, you can calculate the XTCSC, and so your new line reactance X new is equal to your line old reactance. So X line old plus XTCSC. So by this way, you can modify your transmission line reactance. So we will calculate the active power transmission is equal to V1 V2 by X mu sin delta. So by changing this line reactance, you can increase the power transfer capability, right? So by decreasing the value of X mu, you can increase the active power transmission in the transmission line. Now we learn about the TCSC modeling for load flow analysis. So TCSC modeling for load flow analysis. So when we connect the TCSC, at the time the load flow calculation is done by this modeling. So here we use the variable series impedance power flow model. So suppose there is two buses are there. So if the inductive region is there, right? If the only XL is provided, so at that time your modeling is done using this figure. This is your K bus and this is your M bus. And suppose there is a variable TCSC inductance is there, right? So we can calculate the PKM. Okay, this is a figure number A. Similarly, the TCSC equivalent circuit for a capacitive one. So if the capacitive reactance is provided to between the transmission line, so at that time your equivalent circuit is become like this one. PKM. So first figure is for inductive region, second B part is for capacitive region. So the transfer admittance matrix of the variable series compensation, which is shown in figure A and B, is given by I is equal to Y into V. You know that this is a basic load flow equation, right? Where y is your bus admittance matrix, V is your voltage, and I is your current. So how can we calculate the admittance? So from the basic, you know that the y equivalent is equal to G plus JB. So put the value of y here, you will get I is equal to G plus JB into V. So here the G is your conductance and B is your susceptance. But we can consider for load flow analysis only the imaginary part. So therefore our equation is become like I is equal to JBV, where B is your susceptance. So here the two buses are there. One is K and the second one is M buses. So your matrix is become IK and IM is equal to JBK KK into JBKM, JBMK and JBMM. This is the basic of Y-bus matrix, right? Which we already studied in BTech in load flow analysis, right? And the voltage of bus K and M, it is denoted by VK and VM. So this is our equation 1. So for inductive operation, we have the susceptance of the buses is calculated using BKK is equal to BMM. That means the diagonal element is same. It is minus 1 upon X TCSC. And for off diagonal element, BMK is equal to EKM is equal to 1 upon X TCSC. Now what is X TCSC? X TCSC is equal to XL parallel into XC. So that means X TCSC is equal to XL into XC upon XL plus XC. This is equation number 2. This is for inductive operation. And for capacitive operation, this equation is become a reverse. So for capacitive operation, the diagonal element is become BKK is equal to BMM is equal to 1 upon HTCSC and BMK is equal to pkm is equal to minus 1 upon x TCSC. This is equation number 3. So when we put the value of this matrix, susceptance matrix, right, we will get the equation of active power and reactive power. So the active power and reactive power at bus K it is calculated using Pk is equal to Vk into Vm into Bkm into sine of theta k minus theta m. Similarly, Qk is equal to minus of Vk square Bkk minus Vk Vm Bkm cos of theta k minus theta m. And similarly for bus K, bus M, the subscript for K and M are exchanged in equation number 4 and 5. So in Newton-Raphson solutions, these equations are linearized with respect to the series reactance. And for the conditions shown in this figure, where the series reactance regulates the amount of active power flowing from the bus K to M at a value Pkm regular, the set of linearized power flow equation is given by, it is in matrix form. According to the Newton-Raphson load flow methods, it is given by del Pk, del Pm, del Qk, del Qm, and del Pkm x TCSC. It is in matrix. Is equal to, again, so if you know thoroughly the Newton-Raphson method for load flow analysis, you can easily write this matrix dpk upon d theta k, dpm upon d theta k, again d theta k, dqk upon d theta k. So again, the next element is del qm upon del theta k, and last one is a del pkm x TCSC divided by del theta k. Similarly, for a second column, it is del pk upon del theta m, it is for m bus, del pm upon del theta m, del qk upon del theta m, del qm upon del theta m, and last one is a del pkm x TCSC divided by del theta m. Similarly, the voltage, another variable is the differentiate with respect to voltage according to Newton-Raphson method. So our equation is become like del pk upon del vk into vk. Del pm upon del vk into vk. Similarly, del qk upon del vk into vk. Del qm upon del vk into vk. And del pkm x TCSC upon del vk into vk. Similarly, the voltage at bus number m. So they are changing the power with respect to bus m voltage. It is del pk upon del vm into vm, del pm upon del vk vm into vm, del qm del vm into vm, del qk here del vqm del vm into vm, and del pkm x TCSC upon del vm into vm. And now the next variable is change in power due to the TCSC reactance, right? So your equation is become right del pk upon del x TCSC into x TCSC. Similarly, del pm upon del x TCSC into x TCSC. This is in computer matrix, which is called the Jacobian matrix in NR method. Next here is del qk upon del x TCSC into x TCSC, del qm upon del x TCSC into x TCSC, del pkm x TCSC upon del x TCSC into x TCSC. Right? So your total variable del theta k, next is del theta m, next is del vk upon vk, another is a del vm upon vm, and last one is a del x TCSC upon x TCSC. So this is also in a matrix form. So this is your Newton-Raphson matrix, where this central matrix, it is called the Jacobian matrix. So by this way, here the del pkm TCSC and the del pkm x TCSC is equal to pkm regular minus pkm x TCSC calculated, right? What is pkm? It is an active power transmission between bus k and m, right? So your del x TCSC is equal to x TCSC at the current iteration minus x TCSC at the previous iteration. It is an incremental change in series reactance. So the state variable x TCSC of the series controller is updated at the end of each iterative step according to the equation number, this equation. According to this equation, the new x TCSC reactance is equal to x TCSC previous one plus change in HTCSC into the current iteration into HTCSC previous one. So this is your equation number 9. So by this way, you can calculate or perform the load flow analysis, including TCSC in your transmission system. Thank you.